Hey, what's going on, guys? Let's look at this problem right here. Here this question is asking, in the figure, assume that the forward voltage drops of the PN diode D1 and Schottky diode D2 are 0.7 voltage and 0.3 voltage respectively. If on denotes the conducting state of the diode and off denotes non-conducting state of the diode, then in the current, A option is both D1 and D2 are on, B option is D1 is on, D2 is off, C option is both D1 and D2 are off, D option is D1 is off and D2 is on. So here we had to find out which diode is going to be on and which diode is going to be off, or both of them are on or both of them are off. Now let's see what's going to happen. So here they are giving the cutting voltage. This cutting voltage is basically whenever we have the voltage above this one applied to the anode side of this diode, it's going to turn on, right? That's what this cutting voltage represents. Now always we have to look at the lowest cutting voltage of the diode. And if you look at this one, D2 has the lowest cutting voltage. So this is the one that's going to turn on first. So we have to assume that D2 is in forward bias. If it turns on, it's forward bias. So V alpha D2, we have to replace this D2, this diode with a voltage drop. So we are going to replace that one with a 0.3 voltage drop, since the cutting voltage is 0.3 voltages. It's given in the question, right? 0.3 voltage. Okay, now after we replace that one with this short circuit, let's see the new circuit. So we are going to have this voltage plus minus 10 voltage, and here we have 10k ohm, and here we have D1, and this will turn on if the voltage here is above 0.7, right? And we are going to replace this diode with a voltage drop, that is 0.3. okay, now what we are going to do, and also we have a resistance right here, that is 20 ohm. Now what we are going to do is we are going to calculate this voltage across D1 and see whether it is above 0.7 or below 0.7. If it's above 0.7, we are going to this diode is going to turn on, and this is going to be in forward bias. And if it's below 0.7, it's not going to turn on, so this is going to be off. It's in reverse bias. Now let's see what's going to happen. Now to find that one out, we can apply KVL. So VD1 should be equal to voltage across this resistor and also this voltage drop. Voltage across the resistor can be calculated using basic Ohm's law. V is equal to IR. So we know that resistance is provided and the current is going to be same everywhere because this is in series. So it's going to be same everywhere. So we can say I times 20 ohm is going to be the voltage across this resistor. And also we have a voltage drop, that is 0.3 voltage. Okay, now current can be calculated using V is equal to IR. So I is equal to V over R. V is going to be what? Here we have 10 voltage minus 0.3 divided by the total resistance. Here we have, actually this one is 1k ohm resistor divided by 1k plus 20 ohm. So 1k plus 20, 1020 multiplied by 20 ohm. Let's get rid of this ohm. 20 and then plus 0.3, and that's going to give us the voltage here. Now if you calculate this one, this is going to be about 9.7 divided by 1020 times 20 plus 0.3 voltage, and that's going to be 0.2 plus 0.3. So we are getting approximately 0.5 voltage, and that voltage is less than 0.7. That's what we have to get 0.7 right here in order to turn on this diode. So since we have less than that, this is going to turn this one off. So here what's going to happen is D2 is going to turn on, but D1 is going to turn off. So the correct option is D2 is off. Actually D2 is on, we found that's on, and D1 is off, D1 is off, D2 is on. So D is the correct answer. And that's how we do this kind of problems. I hope this helps. Thanks for watching.